So I am actually a storage person, surprisingly enough, although my primary job at IBM as a container evangelist. I got into containers by converting software businesses to open source, and it just so happened that the first company I was really engaged to do this for was a company called Parallels, who'd been doing containers in Linux since about 2001. So I got an early leg up on the container wave, as it were, in Linux, long before it was a wave, in fact, even before it was a little trickle. But because my job was actually trying to get most of what Parallels needed for its containerization technology upstream in Linux, I got to play with it all firsthand, and at the end of the process, I actually ended up a sort of container expert. Other jobs I have in the Linux kernel are SCSI subsystem maintainer. That's the ancient and old block subsystem. And I actually did something with peer risk architecture as well. Peer risk is the old HP architecture, now long since deceased, but it's still fun to play with, and that's really much more of a spare time job. So one of the things that I need you to understand to actually get a handle on this talk is how containerization technology actually works in Linux. So most of what I've heard about at this conference are traditional virtualization technologies, which are based in things called hypervisors and are primarily about getting some software system to emulate hardware on which you can bring up another software system. Containers, as it turns out, are nothing like that. Containers are about virtualizing the operating system itself. And the key thing that is the difference that causes the problem for all of you as storage people is that in a containerized system, the guests do not have a separate kernel. So in a container system, the guests take all of the services from the kernel that's running as the host operating system. So this means that all of the magic storage technologies you did in the past to push storage through the hypervisor into the guest by some sort of hardware interface don't work in the containerized world. So this is an example of what a containerization system in Linux looks like. As I said, containers are about virtualizing the subsystems of the operating system itself. So each operating system to run containers has to have this set of virtualizations present. So this was part of the race to catch up with Windows, because when the container wave first hit in Linux, Windows itself didn't have any of the operating system virtualizations you needed to bring up containers. So they've been rapidly developing them for things like Windows 10 and Windows Server and so on. In Linux, the two ways we do this are with something called cgroups, which are resource controllers. Effectively, they keep an eye on what resources a container is allowed to use, and there are a variety of them in the Linux kernel. And we also have these things called namespaces. Now, listening to all of the presentations this morning, I believe namespaces is a very heavily overloaded term. When you say namespaces in storage, what you mostly mean is a per-tenant area for storing stuff that does not necessarily correspond to the underlying physical disks. So when we say namespaces in Linux, we tend to mean a per-tenant area for doing stuff that is perhaps related to the underlying subsystems of the Linux kernel. So if you think of all of the containerization systems that are run in Linux, the oldest and most venerable is something called LXC, the Linux container system. This has been around effectively since 2006, 2007. So it precedes almost all of the containerization waves in Linux as well. It's based on something called operating system containers. An operating system container is a container that effectively contains a full operating system. You can think of it as infrastructure. The more modern incarnation of containers, the one that is actually popular, is something like Docker. Docker likes to think of itself as an application container, but this is really a lie. Docker is much more an infrastructure packaging subsystem that uses containerization technologies to operate. And then there are they're not quite also-rans yet, but one day they will be, like Apache Mesos. But the point about each of these systems is these containerize in a radically different way, but they all use the containerization subsystems of Linux to do that. There are no ifs, ands, and buts here. The reason this is important to me, and possibly important to you, is because that for containers, we actually finally got virtualization right in Linux. If you go back to the old virtualization where you have Xen, KVM, VMware, each of them actually connects to a separate subsystem in the Linux kernel. VMware is so far advanced now that it's claiming not even to connect to the hypervisor being Linux. But if you go to the two traditional ones, KVM and Xen, we have two totally separate subsystems within the Linux kernel for orchestrating those virtualizations. And this means that if you introduce a virtualization technology into KVM, Xen does not automatically inherit it, VMware does not automatically inherit it, and so on. But it means, because of this single line down here, in Linux, if we introduce additional operating system virtualizations in C groups and namespaces, every container system that's using them can benefit, provided they turn it on. The problem in this statement is provided they turn it on, because container virtualizations are highly granular. Unlike hardware virtualization, where it's basically all or nothing. You either have virtual hardware or you don't have virtual hardware. In containers, we can turn on, just say, one C group, or I could turn on just one namespace. And each of the knobs that controls these C groups and namespaces can be set arbitrarily as well, which gives me a massive multi-dimensional subsystem for actually turning on all of these virtualizations. And what that means is there is no one true description of a container. I can build a container in an uncountably infinite number of ways in the Linux kernel. And all we actually really play with currently today is the way that Docker does it, which is only one tiny little aspect on all of this pantheon of infinity. LXC does it in a very, very different way, and there are a few other containerization subsystems that do it in a very different way as well. But if, like me, you actually want to play with the true basic containerization systems of Linux, you have to deal with these things that are controlled at the kernel level. So these are things like block I/O. The block C group controls I/O throughput. The CPU C group controls the amount of CPU your container can use. Devices C group controls which devices you can see. Memory C group controls the amount of memory your container has, and so on. Networking C group, freezer C group, and so on. We go all through it. My favorite interfaces are much more the namespace interfaces. These are the things which actually separate in a container. So a network namespace is what gives a container separate network access. In fact, the network namespace is pretty dumb. As soon as you turn it on, you drop off the network. The only way you can reconnect to it is by pressing something called a VF device, which is basically something which has two network interfaces at one end. You press one end through to the container, and you pull the other end through to the host, and you attach it to a bridge. It's very simple. The IPC namespace is for System 5 IPC, for those of you who still use it. It allows you either to share your, let's say, IPC shared memory channel across containers, or fully separate it and keep it separate per container. The mount namespace, which is a really important one, is actually what allows you to have a different mount tree inside every container. The PID namespace is what allows you to pretend that you cannot see any process IDs outside of your container, and also that the first process spawned into the container runs at PID 1. This is necessary for operating system containers because init has to run as PID 1. The UTS namespace is for NFS. It allows you to virtualize the host name. And the user namespace is the most fascinating thing of all, because it allows you to pretend you're root inside a container when you're not really running as root. This is the most important namespace because it's what gives privilege to an unprivileged container. And although you might not think that's important if you come from the traditional virtualization world where everybody logging into a hypervisor gets root, if they know the root password, in a container, especially in a Docker container, if you run something called a privileged container where you're running as root, effectively you get hold of the real root. This would be the same root that would actually run inside the host operating system. And that gives you an awful lot of power inside the container, which most of the time, if you're actually using containers in a public cloud, you don't want the users to have. The way we control this in a public cloud, or even in just a fairly safe data center, is to use the user namespace to not give away full root privilege, but to give away something that looks like root, but does not have the entirety of the root privileges. The last namespace to be introduced was in the 4.6 kernel, which now was released about 6 months ago. And it's called the C group namespace. So it's actually used to virtualize all of the C groups, or it will be eventually when it's at its full incarnations. The main thing that most of the people who run orchestration systems will tell you is that these interfaces are very difficult to use. So one of the things I'm here to tell you is that actually then these interfaces are not difficult to use. You don't actually need to use a single orchestration system to run containers in Linux. You can use the operating system primitives themselves, and there are 2 system calls. Actually, now there are 3. There's clone or unshare, which is a separate system call, and setns, and there are effectively 2 user space utilities that allow you to do this. I do actually have a demo in this, but because it's running on a Mac, I'm not going to be able to show you the demo, which is probably good because I'll run out of time anyway. But you'll just have to take my word for it. So when we try and make it all work, we're effectively trying to bring up containers using the user namespace, which is used to do privilege separation to unprivilege what's effectively a privileged container. And user namespaces gives an enhanced privilege to a user, like the ability to create other namespaces or do all sorts of other interesting things inside the container. And it also does a mapping between what we see of as the interior ID, which is the UID you think you are in the container, and the exterior ID, which is the ID that you are in the kernel. And there are lots of proc files that I won't go into that you actually use to do this. And there's a shadow utils, if you install it on your Linux system, that actually allow you to play with this. And it retains the concept in a user namespace of an owning UID, which does not have to be root. So the person who actually created the user namespace actually has the owning UID. So if I create it as my own little JEJB account on a Linux system, I become the owner of that user namespace. And the owning UID is the one that can actually give itself enhanced privilege, root-like capabilities. All unmapped UIDs inside a user namespace are inaccessible. So one of the ways that we cut the user namespace off from the vast plethora of UIDs that might represent your other tenants is by simply not mapping them. So this is another safety feature. So let me illustrate the problem that this actually brings for storage, or one of the problems this brings for storage. In user space, you have a view of the UID, which is what would be the interior UID. So it's the standard one you see. This would be, if I want to pretend I'm root, ID 0. In the kernel, you have an absolute kernel view of what that UID is. So if I've taken my little UID and mapped it into the kernel, I would actually have numbers for this. So it would be about 1,000. And then across the other side of the boundary is where you write from the kernel to the storage. So if we do it with numbers, I'm pretending to be root, so I've got UID 0 as the interior ID. My kernel view is 1,000, and the problem is that because the kernel writes to the storage using this file system UID, which is identical to the kernel UID, the actual ID that this appears on the file system is also 1,000, which is a bit of a problem if I'm pretending to be root, because this means that any unprivileged container that's trying to be root and write out a root image cannot actually do that. So this is a fairly significant problem in Linux. This is the reason why Docker, a Docker privileged container currently has real root running inside it, because the only way it can actually tamper with file system images as real root is if it's 0 here, 0 here, and 0 here. This is one of the many security problems with Docker. The ideal that we'd actually like to do, and that we're actually working on today in Linux, is something called the superblock namespace. So it's a mapping that goes across the kernel to storage boundary. And so it allows us to have the mapping here, which is the user namespace, and the mapping here, which is the superblock user namespace. And it means that I can come in as my interior ID 0 here, go down into the kernel and be seen with my real UID of 1,000, my exterior UID. But when I write to the file system, I write across this boundary where the superblock namespace is, and I get transformed to what looks like an interior ID, and I'm writing at UID 0. And what this would tell us is that this problem is now solved in Linux. It's a superblock namespace. This was actually introduced in the 4.10 Linux kernel, so it should be there already, and it should work. And the problem is that it doesn't. And the reason that it doesn't is because to use it, you need a superblock. which sounds fairly obvious to you as storage people, because every time you mount storage in the kernel, you get a superblock for that mount. The problem is that containers do not usually mount storage. Usually storage is what's called bind mounted into a container, not real mounted into a container. And with a bind mount, you do not get a superblock. So, to go into this in some more detail in the last 5 minutes, struct mount is a file system internal structure, and VFS mount is what is visible. So this thing is actually used, VFS mounts in Linux, what we use to build a file system tree, not superblocks. And a file system tree is just a set of these struct mounts that go all the way on, potentially through the directories. Every time we bind mount into a tree, we just started a new VFS mount. But the problem is that every mount namespace has a set of these struct mounts, but all of these struct mounts point to a superblock, and the superblock system is not virtualized. And the relationship is many to one. So if I mount something external, I get a new superblock, but if I just bind mount it, I get the same superblock with a different VFS mount, and this is the problem. So to illustrate, these are a set, every node in this tree is a VFS mount, and every color on this tree is a separate superblock. So I've got the red superblock here, and I've bind mounted it, so I've got a red superblock here, I've done a bind mount here, and I've got a blue superblock here. If I unshare the mount namespace, I just get an identical tree, so it's completely identical. But now I can actually modify these two file system trees separately. So I could do interesting things like unmount the blue superblock here, but if I've unshared the mount file system, it will actually stay there. This can be really nasty. Let's suppose the blue superblock represents a USB key. So you insert a USB key into your machine, it gets automatically mounted, then you unshare the mount namespace and try and pull the key out. In theory, because the mount namespace has been unshared, I have a separate copy of this superblock that I cannot actually get to because it's sitting inside a container, and the resulting the thing that results is actually an unclean mount of the USB key. Pretty nasty. One of the other things I can actually do in this unshared tree is I can modify the way it actually looks to the bind mount. So I can cut off bits of it, or I can rebind mount it, or I can do lots of other interesting things to it. But the one thing I want is to actually get hold of this mapping subsystem for the containers. So one of the oldest solutions on the books is to use a fuse mount. So fuse is file system and user space in Linux, which effectively does a UID shifting bind mount. It was done by Matthew Partel a long time ago. It actually works, and it simply remounts a subtree with a UID-GID shift going through user space. The problem is that because it goes through user space, it's actually rather inefficient. And it also requires root to mount this. The solution I proposed 3 months ago at the Linux File System and Storage Summit is called ShiftFS, which is effectively an in-kernel UID shifting bind mount that actually has its own superblock. And because it has a superblock, what it can actually do is pick up S-user namespace that it needs every time there is an effective bind mount into a container. It requires the admin to mark which piece of the file system is bind mountable, but after that it can be done fully unprivileged. So you can actually designate all of the storage you want to bind mount into the container and do it anyway. And then the container can remount it. I won't be able to do the demo, but it doesn't really matter because the demo is just going to be a ShiftFS. What actually happened at the Storage and File System Summit in March is that faking a bind mount to get a superblock didn't actually feel like the real solution to everybody, primarily because superblocks are supposed to be one per physical storage system, and this would break the one per physical storage system relationship. The basic question they asked is, can't we just make S-user namespace work as it's supposed to? There was an old proposal, which is the inode view of the user, so UID, KUID, and an inode view, which would actually allow us to do this. It's prototyped using security X attributes, which it makes it seem to work, but it can't be made to work with S-user the superblock user namespace. So the real question that we're having trouble with in Linux is what actually can we do? So this is what we actually see in Linux. A D represents a path, an inode represents an on-disk instance, usually a file or a directory, and the superblock is what actually represents the mount point, and inside the superblock is where this mapping for the user namespace sits, and this is the problem. So what we want to do really is sit inside the VFS mount. And so Ted Cho has actually proposed that we might actually do this. The real problem with this is that this would require the rethreading of almost every VFS call in the Linux file system. So this would be a massive engineering effort on the Linux VFS layer that would basically take instances that speak dentries, inodes, and sometimes superblocks, and we'd have to thread a VFS mount through all of them. So this is not going to be a very pleasant thing to do, and the discussion ended in a lot of finger pointing for who would actually do all of this work. The reason why it's still possible is that because this allows a lot of other properties, labels, to be added per VFS mount. And there are lots of people who are interested in doing that. One of the most interesting things is that because lots of people want to mount Windows file systems, and Windows file systems tend to be case insensitive, whereas Linux file systems are case sensitive, we could actually add a VFS mount flag that allows us to say whether the file system should have case insensitivity or not. And it means that when we're trying to bring up Windows containers on Linux, suddenly we can just use a bind mount label to project the right file system through. The final alternative is to abandon suser namespace arbitrarily, to use this inode mark and just get rid of the user to kernel view. So the conclusions are that we haven't fixed this yet. We're really sorry. Hopefully we'll be there soon. And we have several ways to solve the issue, but we're not actually sure which is the best. And the reality that I owe you a recording, but I'll say it anyway, it's not actually which solution is the best. It's who's prepared to do the work on this solution to get it actually threaded through Linux. With that, I'll just say that if you enjoyed this presentation, it's a web-based one using Impress, which makes me a web developer. And then I'll say thank you and call for questions if I have any.
Thanks very much, James. Now we know the mind of the Linux kernel. We've been exposed to it, so very good. Questions for James?
Did I scare everybody off?
Don, did you get one? Okay.
Sorry, it was a whistle-stop tour. That was an hour talk, I'm afraid.
On the contrary, no. So I've worked for Citibank. We're rolling out containers. Doing persistent storage for containers is a really, really big deal. This is actually one of the best descriptions I've heard of what the real problem is, so thank you very much for doing that. If you had to put your finger up in the wind and say, is there going to be a concrete solution to this in 2018 or 2019? When do you see consensus building around who's going to do the work?
Well, as a kernel developer, I could promise you anything. As an IBM research developer, I know that we want to run a bare metal Docker cloud, the successor to Bluemix, and we want to release that. Okay, I'm not supposed to talk about dates, sometime soon. Before we can release that, this problem has to be solved. So internally within IBM, it has become my job to find a solution to this problem. So I can promise you that this problem will be solved, but I'm not going to say how. One of our options, I have to confess, at IBM is to take what I did with ShiftFS and just graft it into the kernel that runs our bare metal containers and just use that. So I'm not going to promise you this problem will be universally solved, but I will promise you there will be a solution in very short order.
Thank you. Any other questions? Okay, very good. Thank you again, James.